All right, this is chapter 3, and we are going to be looking at vectors. So, the big ideas from this chapter are that a vector has both a magnitude and a direction. We're going to look at how the components of a vector measure how much it extends in some direction. We're going to look at how to add and subtract vectors and their components. We will look at unit vectors, position, displacement, velocity, and acceleration vectors, and then we're also going to be looking at relative motion problems. So what is a vector? A vector looks like an arrow, but it tells us information about what is happening. So this vector has a magnitude, meaning a length. It tells us some piece of information. Maybe it tells us a distance, could tell us a length, could tell us any variety of information. It is a number that has a unit. And then it also tells us a direction. So if it's pointing in the right direction, depending on how you've set your coordinate system, it will tell us if the direction is in the positive direction or the negative direction. The arrow portion is going to be called the head, and the beginning portion is the tail. We talked about scalars versus vectors back in chapter 1, so I hope you'll kind of remember a little bit of that. A scalar is just a number with units, and a vector is that number with units, but it tells us what direction we are going or some particle is traveling. So if I want to know how to get to the library and you say, oh, it's half a mile away, well, that's fantastic, but in what direction? So you will see very quickly that vectors are much more helpful than scalars because they tell us direction. And even though we know how far something is, so we have a vector, we know how far the library is, and we know what direction it's in, we might not be able to walk there in a straight line. So if you look at this example, we see that this vector has us cutting across several patches of grass, and we don't know what's on there. It could be a house. We might not can cut through these people's yards, but we can actually find the horizontal and vertical components of this vector to figure out a way in which we can actually walk to the library or bike or drive, whatever you want to do. I mentioned this, and now we're going to get a little more specific. So this purple vector is actually found by looking at our y and x components. So this vertical vector has only a y component. That is why it is only pointing in the y direction. And this one only has an x component, and that's why it's only in the the horizontal direction, in the x direction. But this vector here, vector C, the purple one, it is going to have both an x and a y component because it is neither horizontal nor vertical. It is in the diagonal direction. And this is going to be true of any vector that lies in a diagonal direction. Any vector can be placed on a two-dimensional coordinate system. And this is something you're going to be doing for basically any problem we work. You're going to want to draw your vector in a coordinate system. It doesn't matter which way you choose to draw your coordinate system, but what you see here, where we have x as the horizontal direction and y as the vertical direction, is going to be pretty common, and that's what I would recommend that you do. So we have this vector here, vector r, and we can actually find the components that make it up. So we can find the portion that lies in the x direction and the portion that lies in the y direction. How do we do that? We use trigonometry. I know it's probably been a while since you've taken trigonometry, but no worries. it should come back to you pretty quickly. So I'm going to show you how to do this. I put a couple of things here. So we see that the x component of vector A is found by multiplying vector A by the cosine of theta, and the y component is found by multiplying vector A by the sine of theta. And this is found by doing SOHCAHTOA. If you remember SOHCAHTOA, we can just rearrange that, and that's how we get those equations. And you're going to want to know those equations. Let's actually look at a problem, though. So in this case, we have a zip line which has been set up from a tree to the ground. And that zip line is going to create an angle of 18 degrees with the horizontal, so with the ground. It is anchored to the ground 12 meters from the base of the tree. So we want to find the height of the top of the zip line above the ground, and then we want to know what length of wire is needed to make that zip line. And the first thing you should do when you begin this problem is draw your coordinate system and then put any information you know on the coordinate system. So take a moment and do that before continuing. All right, I hope you were able to sketch a system. Now, I did not draw this. Y'all saw what a disaster the last video was when I tried to draw. So I have typed or put images. This is a very fancy image of our zipline setup. And yours probably doesn't look quite like this, but you get the picture. And it's okay if you flipped the way yours looks. Maybe your X is over here and your Y is right here. That's okay. As long as you have all of this information, you will be fine. So where do we begin? Well, let's plug in the information we know. We know that the base from the tree base to the edge or the end of the zip line is 12 meters, and we know that it has an angle of 18 degrees. So let's go from there. We need to find the y component. So we want to know in part A, what is the height of the top of the zip line above the ground? So that is this y component. Well, to do that, let's remember SOHCAHTOA. And if you're not sure what this is, S stands for sine, C stands for cosine, T stands for tangent. We find the sine by looking at the opposite. So here's our angle. So the sine would be the opposite over the hypotenuse. Well, that would not help us here because we don't know either of these pieces of information. The cosine, so the cosine of this is the adjacent vector over the hypotenuse. So this one over the hypotenuse. Okay, well, we do know this value, but we're not interested in finding r right now. We want to know this value. So the tangent is the tangent of 18 degrees. It's opposite over adjacent. The tangent has all the information we need. We are looking for ry, and we know the value for rx. So why don't we use the tangent? Okay, so the tangent of theta is ry over rx. And now we can just plug in the information we know. Well, okay, let's rearrange it first, and then we'll plug in the information we know. That makes a lot more sense. When you rearrange this, you should find that ry, so the y component, is equal to the x component multiplied by the tangent of theta. Okay, so our x component is 12 meters, and we have the tangent of 18 degrees. Heads up, please make sure your calculators are set to degrees and not radians. And when you calculate that, you should find that the y component is 3.9 meters. Okay, so now we need to actually look at part B. What length of wire is needed to make the zip line? Well, this is a right triangle. And again, if you think back to trigonometry, if you have a right triangle and you know the length of the x component and the length of the y component, we can use the Pythagorean theorem. So let's do that. For the Pythagorean theorem, remember, that's where we're going to take a squared plus b squared equals c squared, or the x component squared plus the y component squared equals that hypotenuse squared. Or you can use the cosine. It doesn't matter. Whichever you prefer is fine. When you solve this, and I'm going to let y'all plug in those values, you will find the answer to be, and if you don't want to see it yet, pause it. Try it yourself. 13 meters. Okay. And let's look at another problem. So this time we know that we have a vector and it has a magnitude of 9.75 meters. We want to know its components, so the x and y component, for direction angles of 7.25 degrees and 115 degrees. Again, we want to start. I'm sorry, I should not show you that yet. Why don't y'all try to work this one yourself and see what happens? So go ahead and hit pause and be sure you draw that image, that sketch, before you move on. Okay, so here is the sketch. We see that our vector A is made up of an x component and a y component. This is a general sketch. This is not correct. And I didn't draw two separate ones because we see here that this is a very small angle and 115 is a very large angle. So I just gave you a general image. It still works the same. If that was all you needed to get started, press pause again so you can do the math. If not, keep watching. So we need to find that x component and the y component, and I've given you the way to do that right here. We know that vector A is 9.75 meters. And for part A, we have an angle of 7.25 degrees. So let's plug in our information for the x component right here. And that's going to equal 9.67 meters. And we're going to do the same for the y component. So we're just switching out cosine or sine for cosine. And that will equal 1.23 meters. Okay. So if part A was a little bit of a struggle, go ahead and pause and try part B. Okay, here's part B. So now we're just switching the angle. Everything else stays the same. In this case, we have the cosine of 115 degrees instead of 7.25. Ooh, and this time we got a negative value. Yes, that is possible. Do not panic if you see that. And our y component is 8.84 meters. So having a negative value is perfectly fine. If you see this, don't assume your math is wrong. I mean, it's always a good idea to double check, but a negative value is okay. The signs of our vector component, so you saw that we just got a negative value. I'm going to now explain what that means. For the x component, if we have our triangle, you see these are right triangles each time. We want to look at how we're moving towards the right angle. So here, 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 and here. If we are moving towards the right angle and it is in the right direction, then that means we are moving in the positive direction and our x value will be positive. If we are moving towards the left, then we are in the negative direction on the x-axis and our value will be negative. Okay, so in this case over here, this negative 4.12 tells us that this x component is going to lie in the negative x direction. So if we have our system, it's going to lie over here. I hope that made sense. And that brings us to something even more exciting. We're going to be adding and subtracting vectors. We can do this graphically, You're also going to be doing it with actual math, but it's a good idea to draw your sketch first. Anytime you are adding vectors, you always place the tail, so that end part, or I guess the beginning part, of the second vector at the head of the first, just like we see here. So this is the little end part of the blue vector, vector B, and it is touching the head of vector A. And the sum is going to point from the tail of the first, so here's the first vector, so here's the tail of the first vector, to the head of the last. So this is our sum, and that will always be the case. We'll start with that first vector, and it'll start at the tail, and then it will end at the head of the final vector that we are adding. So here we see that vector A plus vector B plus vector C is equal to vector D. And here I'm just showing you something a little bit different. So in this case, we have vector A plus vector B, and this vector C is the sum of A and B. And I'm showing you this because I want you to know that when we're doing vector addition, it doesn't matter if you add vector A plus vector B or B plus A. They are both going to equal C. And I've done that here. So in this case, B came first and A came second, but that did not change vector C. It will remain the same regardless of the order. To add vectors together, you'll have to do this using the X and Y components. Sometimes you'll get lucky and maybe the vectors you're working with will only have an X or a Y component. So those problems will be a little bit easier. But if not, you will have to add all of the X components together and then add all of the Y components together separately. And that will allow you to find the vector, the resultant vector. Okay, let's go ahead and try one. So we want to know the magnitude and the direction angle of the net displacement for the treasure hunt that's illustrated here. So the image is already given to you because you needed all of these pieces of information in order to solve the problem. We want to know the magnitude and the direction angle of the net displacement. Well, in this case, our net displacement is simply the sum of vectors A, B, and C. So it's this resultant vector. Okay, so we're going to have to find the X components and add them together. And then we're going to have to find the Y components and add those together. We know we have to do that because we have 3 different vectors. This is pointing vertically, so it's only going to have one of those components. This is horizontal, so B will have one of those components as well, but vector C will have both components, X and Y, and vector D will also have both components. So let's go ahead and figure those out now. If you want to go ahead and try this, press pause and go ahead and work this problem. There it is again. Okay, otherwise we are going to move forward. So in this particular vector, vector A, we are lucky. It is vertical, so there is no X component. There's just a Y component, and we see that it is 3.75 meters. That's very easy. Okay. Vector B is also easy for the same reason. So this time it's horizontal, and that means it has no Y component, but it does have an X component, which is just equal to its magnitude. Now for vector C, we're going to have to do a little more work because vector C is diagonal, which means it has both an X and a Y component. I went ahead and showed you this just because it is, well, we've already done this a few times, so hopefully you're getting the hang of it. We are going to take our vector C and multiply it by the cosine of 45 degrees, which is our angle here, in order to find the X component. And we're going to do the same, but with the sine of 45 in order to find the Y component. You'll see that we get a positive value for the X component, but we get a negative value for that Y component. And that makes sense because we are moving in this negative Y direction. And now we can solve for the x and y components of vector D. So let's just add together all of our individual components of A, B, and C. So 0 is the x component of vector A, 2.25 is the x component of vector B, and 2.12 is the x component of vector C. And that gives us 4.37 meters for vector D. For the y component, we have 3.75 meters for vector A, 0 for vector B, and negative 2.12 for vector C. So we add all those together and get 1.63. So that gives us the x and y components of vector D. And to solve for D itself, which is the thing we need, we want to know this net displacement. So the magnitude here, we just use the Pythagorean theorem. So D is going to equal 4.66 meters. We are almost done. The last thing we need is this angle theta. And to do that, we're going to use SOHCAHTOA again. And to find this, since we now have all three, you could have used any of these, sine, cosine, or tangent, but I'm going to use tangent here. And we're going to do the opposite. So the y component divided by the x component. When you do that, you should find that your angle theta is 20.5 degrees. And we are moving right along. All right, if we want to subtract vectors, please know that the negative of a vector is going to have the same magnitude. It's just going to point in the opposite direction. So we have our vector B. If we make it negative, it simply points in the opposite direction. So since that's the case, vector D, instead of it being A plus B, it's going to be A minus B. I mean, technically it's still A plus B. It's A plus negative B, which is A minus B. Okay, so let's work a problem using that. And if you want to give this a try on your own, hit pause and then play when you're ready. So for vectors A and B here, we are actually going to find D, and you'll notice D is not shown here. So D would be the vector that would happen if we took B and we flipped it around in this direction. I don't think I can. No, I cannot draw on here this time. So if I want to do that, okay, so if we wanted to know what exactly vector D is, it would be us taking vector B, flipping it in this direction over here, and then D would be whatever started here at the origin and connected to the head of vector B. So we're going to solve for this the same way. We have to find the x and y components. So we knew that vector A had a magnitude of 5 and B has a magnitude of 4. We're going to solve for those x and y components of A first, and then we're going to do the same for vector B. Okay, so when you do that, you're going to find these values. And we're going to solve these the same way. And remember, this is just our generic equation. We're going to use whatever the magnitude of B is and then multiply it by either the cosine or the sine, depending on if we're looking for x or y, of the angle theta. Okay, so you see the values that you get over here. Finally, we can solve for the x and y components of vector D. So we can't just jump to find D yet. We're going to have to add together those individual components. Well, subtract the individual components. And you'll find that 2.50 meters. So the x component here, we're going to subtract it from the x component here, and we get negative 1.26 meters. We'll do the same thing for the y component. You'll get 2.96 meters. Okay, so that is the x and y components. But we need the actual magnitude of vector D, not just the x and y components. So there are your components. Hit pause if you want to solve this yourself. Okay, we're going to use that Pythagorean theorem again. which is going to give us a value of 3.22 meters. And from there, we will be able to actually solve for theta. So I'm going to use the tangent again. I just like to be consistent. And when you use the tangent here, you are actually going to get a negative angle. So we don't want a negative angle. We know by sketching our system, if we flip B and make it negative, we are going to end up with an angle that's somewhere in this section. So we're going to need to add 180 in order to get that final answer. And when you do, you'll find that your final answer is 113 degrees. Okay. So that is what it would actually look like after. And you've already seen this image.